Just now.
I wonder if that was just because it was launching?
Yeah.
It didn't go black though, did it?
It did.
It went black?
And then green.
And then green? And then back to black?
Yep.
Really? I missed it. But it did not do that Tuesday. That we noticed. Okay, well, we'll have to watch for this flickering business. Somebody sent me somebody in another classroom actually videotaped it on a phone, so I sent it to IT because they're like, it's not that important. It's just a couple seconds. Hopefully it doesn't happen to us. We'll see. We also had the lights out on Thursday. Maybe that's it.
That's just conspiracy right there.
Right? Right? Okay. Yeah, that seems a little far-fetched. Okay, so we were at the point we had done, I just left that page. So we were doing these problems where we were given either acceleration or velocity, and we were trying to get the position. So the sequence that we want to remember is that you can go back and forth between acceleration, velocity, and position. And if we're going this direction, we are going to be integrating. So if we have acceleration, we integrate once, we get to velocity. We integrate a second time, we'll get to position. So that's kind of the sequence that we were using on these problems. Now, in this application, they have generalized it, and we're no longer dealing with those three physics quantities. We just have the rate of change of a population, and we want to use that information to predict the population in the future. So we're going to use the same concept, though. It's just that we don't have those three letters anymore. So this is a super common application that you would see. You can go out into nature and you can measure the rate at which something's changing, whether it's a population or some flow of water or flow of electricity or whatever. So this is a very reasonable type of thing that you could go measure out in the world. But we want to then use that to predict the future. Predicting the future is how we get rich. If you can predict the future, you can make money. So predicting the future is super important. So let's predict the future here. Okay, so we've got this fluctuation, 10-year cycle, deal the variation of praise. We're dealing with foxes. There's the rate of change. So let's start with that. So the future population, let me say one other thing here. This is kind of backwards in my mind. It says, what's the population 15 years later? And then it tells us to find P of t. The natural thing would be take your derivative, find P of t, and if you want the population 15 years later, what do you do once you have P of t? Plug in 15. Right? If we build the function first, if we build P of t, then we plug in 15, and that will tell us the population 15 years into the future. So our P of t, this is going to be, actually I see that the earlier calc class has this up on the board. This is that generic relationship. So the population in the future will be the population at time 0. So the population that is sometimes referred to as the initial population. So P of 0 plus the change in population. And the change in population is the integral of the derivative. The integral of the derivative, that thing, is what gives us the change in population. So we're going to go from 0 to t. And as soon as we see this t in the integral, in the limits of integration, we know that that thing is a function. It's not a number. Remember that if you do a definite integral with two numbers, that whole thing is a constant. But here, if you have an integration limit that's a letter, that means that thing's a function. It's going to change as t changes. It's a function of t. Now we need an independent variable here for the dummy variable, and we want to just use something other than t because t is already used. You can use your favorite letter, whatever floats your boat. Okay, so that's our generic formula. That's our setup. So P of 0, we were told at time 0 we have 35 boxes. So we're just going to plug this stuff in that we know. So we're going to have 35 plus the integral from 0 to t. And here's where we're going to plug in our derivative function. We need to use a letter other than t, so we'll be using x. So there is our setup. That look okay to everybody? Holler, yell, throw something if you have a question. Whoa! So then, we know how to integrate 5. Integrating a constant just integrates to the constant times the independent variable, so that's going to be 5x. Now we have to integrate this sine business. And notice that the angle is linear. Right? That's a linear function of x. We have a constant, pi over 5, multiplied by x, mx, right? mx plus b, b is 0. So when we're integrating and the angle is linear, we can use that expression I used last time, reverse chain rule, RCR. Because this is linear, we know that we can do, instead of doing substitution, we can do substitution without substitution, which we call the reverse chain rule. So because that's linear, we can do RCR. We can do the reverse chain rule. So we're going to come in there. The integral of the sine function, so we sort of think about the constant in front, that's just going to come along for the ride. Then we've got the function. The integral of the sine function is negative cosine. So integral of sine is negative cosine. So we're going to go, okay, negative cosine. So we'll have negative 10 cosine. When you differentiate or integrate, the angle doesn't change. The angle stays the same. So we're still going to have pi fifths times x. Okay. So now we've dropped the constant, we've integrated the function, and now we zip into the function to the angle, and we have to deal with the angle. What is the derivative of the angle? What is the derivative of that linear function?
Pi over 5.
Pi over 5. Right? That, if we were to come off to the side and write it, kind of at old school, we'd say, oh, that's y equals pi divided by 5 multiplied by x. The derivative of a line is the slope. Right? Derivative of a line is the slope. So y prime is just pi fifths. Okay, so that right there's the derivative. And when we do reverse chain rule, what do we do with that derivative? Divide by it. So division by pi over 5. And then we put our evaluation symbol, 0 to t. And we remember, please remember that the antiderivative that gets the substitution of the t and the 0, it starts with this plus 5 business, right? It's all this. That's what gets the substitution, not the 35. The 35 is sitting out in front. That's separate from the antiderivative. So that 35 is just sitting there. Plug in the t. So we're going to have plus 5t. And now we plug in the t into this cosine function, so we'll have pi over 5 times t. But the coefficient, dividing by a fraction, we multiply by the reciprocal. So we'll have 50 over pi. So we're going to have minus 50 over pi times cosine of pi times t divided by 5. So that's the upper limit, antiderivative at upper limit. Any questions on that? So when we do the fundamental theorem of calculus, we take our antiderivative, plug in the upper limit, and then we subtract off the antiderivative at the lower limit. So subtract off the whole green piece at 0. Well, 5 times 0 is 0. We plug it in here. Cosine of 0. Unit circle. Angle of 0. Cosine is the x-coordinate. 1. So that whole piece is going to be 1. So we're subtracting off this. I'm going to put parentheses here just to help avoid distribution issues. So subtracting off green, evaluated at 0. 5 times 0 is 0. We still have that minus sign. We've got the 50 divided by pi. And that 50 divided by pi is multiplied by a 1. So that would be antiderivative evaluated at 0. And now we just have to collect like terms, if there are any. Over here, we just have a constant. We're going to have plus 50 over pi. Let's just pull that all the way out to the front and at least group it next to the other constant. So plus 50 divided by pi. All right, so that's all taken care of then. That's right there. And then we have the other part of the function. We have the linear part of the function. And then we have the trig part of the function. And there we have it. So now we have our function. So we called it P of t. So we did all this stuff to get to a simplified version of P of t. So this tells us our population at time t, where t is some, years in the future. And they are asking us in particular for P of 15 and P of 35. So if we want to evaluate and figure out P of 15, all we have to do is plug in the 15 and then simplify. I'll write it out here, but maybe I just won't do the simplification part because you can simplify this. Plug in 15 there, we get 15 divided by 5, so we get cosine of 3 pi. And what would cosine of 3 pi be? So we've got our unit circle. You should be visualizing your unit circle. 0 degrees is here. 1 pi, 2 pi, 3 pi. Cosine would be -1. So that whole part right here, this part is going to equal -1. And then you simplify that. Multiply the 5 times the 15, add it to the 35. That's not too much. And then very similar for P of whatever the other year was, I think it was 35. Same idea. Just replace the t with 35 and do any simplification that you can do. All right, any questions on any of that? Yeah?
Do you care about how we format our equations?
It depends on what you mean. What do you mean?
Like some teachers, when it's long strings like that, they want it like highest degree.
No, I don't care about that. I don't care about that. Yeah, that's up to you. Yeah. If you like to write, so it's going to be interesting because traditionally we sort of write things in descending out in order, descending powers, like x squared plus x plus 1. But as soon as we get to infinite series, we write them the other direction. We're going to see that an infinite series is going to be written with the powers increasing, which makes sense because the powers are going to go on forever. So it makes more sense to write them in increasing order. So it's not going to matter to me if you write increasing or decreasing. That's fine. Equal is equal, right? Equal is equal. So last slide in 6.1 is just this summary slide. That's that equation that was left on the board earlier. It's down here. That's just the generalization of this whole idea. That you can predict the future by noticing how quickly something is changing in the present. That's what we're doing. And the bigger picture of that, which we'll get to in a few chapters, is solving a differential equation. So when you're looking at rates of change, you're creating something called a differential equation. Differential equation. There it is. It's flickering. Okay. Now I saw it. So what we're going to do at break, I'm going to log out at break, and we're going to put the monitor on first, because that's the only thing that I've seen that is different. Because I know on Tuesday I put the monitor on before I put the computer on. That would be so cool if we could figure it out without IT. Okay, 6.2. 6.2. So this should be semi-familiar from Calc 1. You know that the area beneath a curve, if you just wanted the area beneath the black curve there, so, and when we say area beneath the curve, you know, we're talking beneath the curve and above the x-axis. If you just wanted that area, you would integrate the black curve, right? If you wanted this area, you would integrate the function and multiply by -1. That would give you the area. Area is always positive or non-negative. Area is greater than or equal to 0. All right, so what we're thinking about here then is kind of combining this into one problem. And what I mean by that, my yellow is there. Well, it doesn't matter. Actually, that was fine the way it was. So, okay, so if we want the area between the curves, back in Calc 1 you learned this really exciting process called the Riemann sum. You know, you found a left endpoint, a right endpoint, you bisected the interval, and you found a sample test point from all the subintervals, and then you added them all up, and then took the limit. So fun. I'm sorry to say we are not doing that in this class. In this class, we just go and wave our hand. We do not go through that miserable process. So, but the idea is what we want to think about and make sure that we are understanding the idea. So the idea, if we wanted the area beneath these two curves, we're just imagining a sequence of rectangles, and we're going to find the area of each rectangle, add them together, and then we take the limit and sort of force all the rectangles to become infinitesimally thin. That's the idea behind the Riemann sum. So if we look at these rectangles, the height of any one of these rectangles is the upper curve minus the lower curve. Anytime you want to find a vertical distance, you take this y value, the higher y value, and subtract off the lower y value, and that's going to give you that distance. Right? So that's going to be the height of the rectangle. The height of the rectangle is going to be the upper y value minus the lower y value. So right here, this is height of rectangle. And then the delta x is just the width of that interval, which is the width of the rectangle. So if you take that right there and you imagine that as the width of the rectangle, you can see that in this summation, we are just adding, right, that summation sign, sigma, capital sigma, S for sum. We're summing all of the little rectangular areas. And then, so that's the Riemann sum. Then you take the limit of the Riemann sum, and the limit of the Riemann sum, that's what you learned in Calc 1. The most incredible thing imaginable is that the limit of a Riemann sum will turn into, what's on the next page? An integral. Right? The limit of a Riemann sum is an integral. So that is the cool, amazing thing from Calc 1 that you learned. And so when we look at this, we just sort of visualize all these rectangles. We create that. That's what it looks like. The area is going to be approximately equal to, if you pick n equals 100 or 1,000 or 1,000,000, it's approximate. And then bada bing, here we go. When you take the limit of that Riemann sum, it turns into an integral, and it becomes the exact area, not an approximation anymore. When you let the number of rectangles go to infinity, and simultaneously the width of each rectangle is going to 0, we get the exact area. So that's our formula for the area between two curves. And when you're looking at this, there's going to be a couple of things, a couple of ways to sort of keep it straight in your brain. You can look at this integral, and you can say, okay, this is going to represent the height of a rectangle, and this is going to represent the width of a rectangle. Okay, so h times w. And then the s, the integral s, also for summation, for sum, So the capital sigma is an S for sum. This symbol for integration is also an S for sum. So you're adding up all of these rectangles to get the total area. That's one way to think about what's happening inside that integral. And if you're going on in physics and engineering, that's quite common to interpret every piece of what's inside the integral with some physical interpretation. That's a super common interpretation. Another way to interpret the integral is to not think about this W and to think of it more like this. You think of the integral and the differential as one symbol, and you stick the function into that one symbol, and you integrate. And if you integrate a distance function, height is distance between the curves. If you integrate distance, you get to area. And we will learn very shortly that if you integrate area, you get to volume. Let me show you a simple example. What is the area of a circle? Pi r squared. What is the circumference of a circle? Do you see the relationship there? If you integrate this with respect to r, you get that. If you differentiate this with respect to r, you get that. If you integrate the formula for the circumference of a circle, you get the area. If you differentiate the area, you get the circumference. And the same is true when we go up another dimension. If we talk about the volume of a sphere and the surface area of a sphere, most of you probably can't remember the surface area formula for a sphere. Probably not. Anyone? What about volume of a sphere? 4/3 pi r cubed. That is the volume, 4/3 pi r cubed of a sphere. No one can ever remember the surface area, but we don't need to remember it because we know how to take a derivative. What's the surface area of a sphere? 4 pi r squared. Just differentiate that with respect to r. So this is a second way to conceive of what an integral means. You integrate distance, you get area, kind of like this thing over here. Now you integrate acceleration, you get velocity, you integrate velocity, you get position. Same idea. You integrate distance, you get area. You integrate area, you get volume. So you can think of the integral in those two different ways. Whatever makes the most sense to you. Somehow you have to organize all these crazy symbols and things, and there are different ways to do that. All right, so here we are, hanging out with these two curves, and we want to know the area between them. So what we are going to do is draw a vertical, I'll call that an integration element. And what you should think of when I say integration element, you think of a rectangle. Right? That's just a tiny rectangle. And all that rectangle does is gives us a way to create the integral. We look at that rectangle and we say, oh, the height of that rectangle is going to be upper curve minus lower curve. That's going to be the height of the rectangle at any x value. Upper minus lower. And then we think of the thickness of that rectangle as the dx. The width of that rectangle is the dx in the integral. Okay, now, when we do our integration, we are going to have a start point right there, which appears to be x equals 0, and a finish point right here, whatever that corresponding x value is right down there. So we're integrating on this interval a to b, where a and b are the x values of the intersection points. So now we have to do a little college algebra. We have to remember how you find where two curves intersect. Well, we set them equal to each other. So do what we always do. Set the curves equal to each other. So minus x squared plus 4x equals x squared minus 2x. So we're just going to solve that equation and figure out what the x values are at the intersection points. Basic algebra principle. If you're solving an equation that's non-linear, that's not linear, we got a square in it, everything to one side and factor. That always works, right? Non-linear, everything to one side and factor. Linear, you put the x's on one side, the numbers on the other. But non-linear, everything to one side and factor. Doesn't matter which side you put the 0 on. Might be easier to put it on the left in this case. So then we have a positive there, and so I did my arithmetic right. That is the equation. So non-linear, everything to one side and set it to 0, and then factor. Or we could just divide out the 2. The 2 does not matter, right? We can divide by a constant. That's fine. We can do that. Now we factor. We've got a common factor of x, so it comes to the front, and we're left with x minus 3 as the second factor. So what does this tell us the x values are? 0 and 3. Zero product rule. Zero product rule says if a product is equal to 0, one of the factors must be 0. Okay, so now we know that this x value is at 0 and this x value is at 3. So we're good to go. So now to find the area will be the integral. So you can think of it again as a distance function. Integral of a distance function gives us area. Or you can think of it as the sum of a bunch of rectangular areas. Whatever you want. So now we have to do the upper curve minus the lower curve. I think the upper curve is that one on the left there. Okay. So it's going to be minus x squared plus 4x. And then we're subtracting off the other curve, so minus x squared plus 2x. So upper minus lower.
Would each function have parentheses around it, so that negative would apply?
The negative I distributed already.
Oh, okay.
Right, so if I subtract off this function, that's going to be minus x squared plus 2x. So if you didn't distribute the minus, right, sort of as you're writing it down, then yeah, you would want that in parentheses with the minus out in front. That's right. Let's just combine the like terms inside this integral before we do the integration. It's always easier to simplify inside first. Yes, if you wanted to, you could factor out the 2. Doesn't matter. I'm not going to factor it out, though, because we'll just have to distribute it again later anyway. Let's just integrate. So negative 2x to the third. So we add 1 to the exponent, and then we divide by the new exponent. So 2x cubed divided by 3. 6x squared divided by 2. And that's on the interval 0 to 3. That thing is a 0 there. Plugging in 0 is not going to give us anything, right? So we can focus totally on the other part. So we're going to have negative 2/3 times x cubed. All right, that's 27. Plus 6 divided by 2 is 3. And then we're going to have x squared, which is 9. So that's what we're going to end up with. So it looks like negative 18 plus 27. So that'll be the area between the two curves. So upper minus lower times dx. Let's try a second one. Unless someone has a question. Yeah, question.
If we had a question like this on the exam, would you want us to put like 9 units squared?
No, only if the problem actually used some sort of units in it.
Okay.
If it's just pure math without any units, you don't have to. Yeah, good question. Yeah, question.
So if it's on the test and you have like a long string of like numbers, do you have to like get the answer, or are you fine with a string of numbers like towards the end?
So are you asking whether it's okay to just leave it like this? No, you have to get to that number.
Okay.
Yeah, you have to get all the way to the final simplification all the way for full credit. If your goal is like, if you just want to see, and you're like, yeah, I'm not going to write any final answers down, you can just always stop in the middle if you want. If that's your goal.
And then our calculators are out.
Whoa. can't wait to break to see if our technique is going to work. Calculators, for exams, you can use scientific calculators. No graphing calculators. Graphing calculators, you can store thousands of pages of notes in.
When it comes to simplifying, do you want us to simplify radicals in fractions as well?
Radical, you can't have two radicals, but it's fine if you have just one radical top or bottom.
Okay.
Yeah, but you just don't want to have two, one up top and one down below. All right.
If you simplify, but you simplify wrong, do you still get partial credit?
Oh yeah, yeah. When you look at the grading guidelines, I'll take off 1 point per trivial error. So if you make some simplification, tiny mistake, 1 point off. Which may sound like a lot, but when we talk about the grading system I use, you'll find that that 1 point is very, very small. And for a conceptual error, I'll take off 2 points. So for every conceptual error, 2 points. For every trivial error, 1 point. But we'll talk about it in detail when we get close to the exam, which is a ways away. Okay, so now we have this other area that we want to find. And we're going to do the same thing. We want to create little rectangles, at least in our head. We're imagining this sequence of rectangles all the way across. And the height of the rectangle, that's the important thing, right? That's the upper curve minus the lower curve. So the integral here will be the integral from, again, it appears to be 0. We don't know 100% if that's 0 or not yet, but it appears to be 0. Depends on the resolution. We'll assume it is 0 for a moment. So same idea though, this curve is just intersecting the x-axis in 2 places. Let's figure out where it's 0. Okay, well the curve is already factored for us. If it's already factored, that makes it easy. This tells us that cosine of x minus 2 is equal to 0, which means cosine is 2, or sine of x is equal to 0. So these are the 2 possibilities, correct? And how frequent is cosine equal to 2? Not very frequent, right? Cosine wobbles around between -1 and +1. So it never jumps all the way up to 2. So that one has no solution. So the only thing we have to worry about is sine of x equal to 0. Whenever you're solving one of these basic trig equations, basic trig equation means sine, cosine, tangent equal to a constant. That's a basic trig equation. 99% of the time, you should draw a circle. If you're trying to solve a basic trig equation, 99% of the time, drawing a unit circle is the move, because you'll be able to see the solutions and hopefully extract them from that unit circle really easily. So sine is the y-coordinate, and we want the y-coordinate equal to 0, so we have those 2 solutions if we're looking at one pass of the circle. So if we write our solutions in general, we would write this as k times pi, where k is an integer.
Is that x equals k times pi?
Yes, sorry. Yeah. Yeah, that is an x, believe it or not.
Looks like yeah.
I know, and it looks like, yeah, or something worse. Okay. So, all right, so we've got in any basic trig equation, most basic trig equations have infinite solutions. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, negative pi, negative 2 pi, negative 3 pi, all those solutions. When we look here, we say, okay, looking at this equation, this looks like the first solution at 0, and this is going to be the next solution. The next solution when we plug in our integers is going to be at pi, right? There's no solution in the middle there. So we're looking for 2 consecutive solutions. The 2 that match are 0 and pi. So those are going to be our limits of integration. So now we're ready to integrate. So our area will be the integral from 0 to pi. Upper curve, what's the upper curve here? 0, y equals 0. Right? Y equals 0 is the x-axis. That's the upper curve. So 0 minus the lower curve. So 0 minus, and I'm going to put the lower curve in parentheses here because I want to distribute here. We're going to need to break this apart. We're going to need to write it like that. So 0 minus the lower curve. For the lower curve, we're just going to distribute signs so that we can then separate everything and integrate. One more simplification step here. We're going to go 0 to pi. That's going to be plus sine times cosine, so sine, cosine. And I'm going to break this apart into two integrals. So that one, because they're going to be done slightly differently. And then this minus distributes over to here, and we have plus integral 0 to pi still, and that's going to be positive 2 sine of x. Yeah?
Shouldn't that first integral be negative since the x getting distributed?
This, yes. Thank you. So that negative distributes to this and makes it negative, and the negative distributes over there to make it positive, 100%. Okay, that second integral we do immediately, right? We know the antiderivative for sine. The first one, though, we have to use our famous technique from Calc 1 called substitution. So when we look at this, we should see two factors. So maybe you separate them like this. There's different ways to look at that minus sign. You could factor the minus all the way out to the front if you wanted. Substitution works best if you can take part of the integrand, let that be u, and if you can pick a part whose derivative is the other part, it's going to be really easy. So is there a u there that we could choose that's going to give us the other part as its derivative? U equals cosine of x. We let u be cosine of x, then du is the derivative of that, which is minus sine of x times dx. There we go. So if we let u be what's the pink one there, then du is going to be minus sine of x, also with the dx. So minus sine of x dx, all the yellow, that's going to turn into du. All that yellow will be du. So we're going to have the integral. We've changed the letter from x to u, so the limits of integration must change. So we're going to have u du. Uh-oh. Oh, at least it's only one of those. It's not like one of the expensive ones. And what are the limits of integration? Okay. Well, the ux relationship is right there. That's how you exchange x's for u's. If you want to put that x into here, it's going to turn into a u. So when x is 0, cosine of 0 is 1, so u is going to be 1, corresponding u value. Make sense? So if we take these right here, it's not explicitly stated, but it's understood. These are x values, right? These x values are coming from this right here. That's an x. So that tells us that those are x values. So if we take x equals 0 and we plug it right in here, cosine of 0, unit circle, 0 degrees, 0 radians is over here, x value is 1. So that's why that's going to be a 1. Same thing for the upper limit. We plug in a pi right there. Cosine of pi, we go to the unit circle. Pi is over here. X value is negative 1. So that's going to be a negative 1 up here. And then we integrate. And we'll deal with the other one in just a sec. Let's just finish this one off. So this is u squared over 2 from 1 to negative 1. Plugging in negative 1 is going to give us 1/2, and then we subtract off what we get when we plug in 1, which is also 1/2. So the total value here is total value would then end up being 0.
Jim.
Thinking of it geometrically, parabola, right? Parabola. And then we are integrating it from -1. If you think about this interval, is that going to help us? If we think about, yeah, that might not help us. And maybe trying to think of it geometrically is maybe not so easy. It's pretty straightforward just to do it analytically. Plug in the -1, you get a half. Plug in the 1, you get a half. Take the difference, you get 0. Okay, let's take a look at this other piece. So we kind of ignored this other integral here. This one is pretty easy though because we know the antiderivative straight off for sine. We just talked about it a moment ago. That's negative cosine of x. And that's going to have limits of integration from 0 to pi. So we're going to have -2. I'll just write it out in gory detail. And you tell me if you agree with that statement. So I'm plugging in the upper limit. And then I'm going to subtract off the antiderivative at the lower limit. So the antiderivative is just this pink part right there. So evaluate it at pi, evaluate it at 0, but take the difference, which changes the sign. And what is cosine of pi equal to? Cosine of pi, -1, x-coordinate at pi. So that's -1 multiplied by -2, so that's going to be a +2. Cosine of 0 is 1, so we get 2 plus 2. So that is our area. And as you do, bless you, as you're doing these types of things, you've all used, most of you have, I would imagine, used Desmos before. Desmos.com. Just type integral, double check your work. You can double check all your work by just typing. Everyone know how to use integration in Desmos? Just type int and the integral symbol pops up, put in your limits of integration, type the integrand, put a dx, and it will give you the same answer that we just got. Page 3. Find the area between the two curves. Okay, a little more trig. Calc 2 and Calc 3 are heavy, heavy, heavy on the trig. So again, if you're not up to speed on your limit, your unit circle values, start writing down sample unit circles and get familiar with those values because you don't want to be spending time, figuring out sine and cosine of all these values from scratch. You want to sort of be able to be efficient. So the area bounded by cosine and sine between these two x values. All right, well, let's go ahead and sketch a graph. So we know that, we'll just start it from the y-axis over. Cosine starts up and finishes up if you look at one period of it. So cosine looks something like that when you go 0 to 2 pi. Sine is off by a little bit. Let's not use black, let's use green. So sine is going to be, let's see, I'm going to draw the midpoint right there. So sine, so that I can hopefully draw it fairly reasonably. So there's pi. Okay. So there are our two curves, and it says find the area in between the two on this particular interval. Well, again, we need to make sure that we understand where those two curves are intersecting. So let's check. So if we set these curves equal to each other, we want to solve that trigonometric equation. That's a pretty easy one to do by inspection if you just look at the unit circle. So if you want to do this one by inspection, not a big deal. Sine and cosine being equal will put us on this line right here. Right? That's the line where y is equal to x. Y equals x. So these are the two positions on the unit circle where y and x are equal. So you can think of it that way by thinking of it geometrically from the unit circle. Or you can solve this trig equation using techniques from pre-calculus. You would divide both sides by cosine. You get tangent equals 1. And when you have a big, crazy trig equation thing, the whole idea is to try to break it down into simple trig equations. There's a simple trig equation. A basic or simple trig equation is where you have a trig function on one side and a constant on the other. And that's as basic as it gets for a trig equation. And lo and behold, those are the same 2 points where tangent is equal to 1. Right. And also notice on the unit circle, isn't the slope of this line 1? Right? Tangent measures the slope of the terminal ray when you're on the unit circle. Tangent is measuring the slope of the terminal ray. Okay. Oh, that's pi over 4 right there. Perfect, because that's what they gave us, pi over 4. So that point right there, that's at pi over 4. How convenient. And this point is at down here, 5 pi over 4, 1 pi over 4, 2 pi over 4, 3, 4, 5 pi over 4. So that is at 5 pi over 4. So they happen to give us the zeros. We didn't know that ahead of time probably, but now we see that the 2 endpoints they gave us are actually just the zeros. So now we're good to go. So our area will equal the integral from pi divided by 4 to 5 pi divided by 4. Upper curve. Which one's the upper? Cosine. Everyone agree? Green is cosine?
No, sine.
Ah, okay, sine. Green is sine. Sine minus cosine? So let's draw a representative rectangle, an integration element right there. So the lower curve is the red one, the upper curve is the green one. So that's the height of a rectangle. So green is on top, and green is sine. So green is sine. So let's go sine minus cosine. Both of those have antiderivatives that we can write down immediately. The integral of sine is negative cosine. Integral of cosine is sine. And we're going to go from pi divided by 4 to 5 pi divided by 4. So we've got that. Whew. All this trig. Now we've got to evaluate these trig functions. Well, it's nice that we have this picture because we can visualize it pretty easily. At 5 pi over 4, we're right down there. What's cosine of 5 pi over 4? Hint, it's negative.
Negative root 2 over 2.
Negative root 2 over 2. Right. So cosine, its first coordinate's always c comma s. C comma s. That's negative. We're bisecting those 2 bisection terminal rays. All will have root 2 over 2's. So it's going to be negative root 2 over 2, but then we have to multiply by negative 1, which makes it positive root 2 over 2. How about sine of that right there? Also negative root 2 over 2? Also negative root 2 over 2, but there's a minus there, so it's going to be plus root 2 over 2. And then we subtract off, so that's antiderivative at upper. Now we do antiderivative at lower. After the minus sign, we can distribute the minus as we go. So cosine of pi over 4 is positive root 2 over 2. And we have minus a minus, which is going to be plus. So we're going to get plus root 2 over 2. So we're subtracting this off. So now we're going to subtract and distribute that minus. That's going to make this positive sine of x. So positive sine, again, we get root 2 over 2. So we get 2 root 2. When we add all those root 2 over 2's together, we've got 4 of them. Root 2 over 2 plus root 2 over 2 4 times is 4 root 2 over 2. 4 divided by 2 is 2. All right, you all try this one. Number 49 is for you, from me. I'll come around and help you if you're having any trouble. Is everyone okay with the trig one here? Can we vanquish it? Everyone know how to add? Okay. So try number 49. Let me know if you need a nudge. Maybe I'll take roll. Now that hopefully everyone knows coming is coming. We still have 2 MIAs. Daniel.
Right.
Jordan. Jordan? Oh, someone that was here last time. Ryan? Lauren? Darla? No. Caitlin Felton? Aiden? Maddox? How you feeling? That's crazy, isn't it? I remember when my kids got their wisdom teeth, we took videos of them because they were so goofed out. It's such a crazy experience. Harrison, Caitlin Hayes, Landon. No Landon? Let's see. Alex Moffat. Hui. Carter. Jose. Yanel. Anna. Gage. Alina. Ari. Austin. Deepa. Arenas. Did I say that right?
Yeah.
No. Did I? Arenas? All right. How's it coming out? No idea how to start. From the beginning. Draw the graph. In math, as soon as you're stuck, draw a graph. Just start drawing things. The sketch, a lot of times, it's not asking you to draw the sketch, but a lot of times with this Calc 2 business, having a sketch is going to really just sort of direct you. So if you're ever not sure, that's the first thing you want to do is draw a sketch of that graph. And how about the second function? Did you draw it in there? I can't tell. Oh, no, you did draw it, yeah. So y equals 4. So draw that. That's not y equals 4. That's y equals x if it goes diagonally like that. So y equals 4 is telling us all the points where y is 4. Right? So if we've got that, so y equals 4 is just going to be totally horizontal. There we go. All right, I'll start it up here. We'll see how far some of you have gotten. So the region because they're saying just quadrant 1, I'm going to draw just the right side of this thing. Now one thing, you haven't drawn a lot of these types of graphs in the past. Maybe a couple. Like if I asked you to do square root of x, is everybody comfortable with square root of x? Square root of x is going to look like a bird wing in quadrant 1. That's going to be square root of x. That's what, if we're only looking at quadrant 1, anytime you have a rational exponent that's less than 1, 1/2, 2/3, 4/5, 6/7, 11/19, they all look like that. If you're in quadrant 1 and the exponent is less than 1, you have a fractional exponent, you're always going to get the bird wing in quadrant 1. That just looks like a bird wing. You're going to always get that type of shape in quadrant 1. So if you've got a fractional exponent that's less than 1, and sometimes on the other side it's going to look symmetric, and sometimes it's going to go below the x-axis, depending on whether what's even and what's odd. But we don't care. For us, most of the time we're looking just at quadrant 1. So in quadrant 1, x raised to a power less than 1 is going to be a bird wing, all right? Fractional exponent. And then y equals 4, when you're graphing, one important thing when you're graphing is to think about the variables in the system that you're in. We're in the xy plane. That equation has just a y, it has no x. So, okay, if y is 4, then we're going to go to, say, 4 on the y-axis. And then you need to know where to go from there. Well, if there's no x in the equation, it means x can be anything. So x is missing, so x can be anything. The equation restricts values, and if x is not there, there's no restriction on it. So we call this process extrusion. So we're going to extrude in the direction of the missing letter. And what's important about that is when you get into Calc 3, if you were to graph x equals 4 in Calc 3, you would get a plane. X equals 3 would be a plane, whatever, x equals 3 would be a plane, y equals 4 would be a plane, because 2 letters would be missing, so you would extrude in 2 directions. So whatever letter's missing, you pull the graph in both in that direction. So here the x is missing, so we pull in the x direction. So it says find the area between the 2 curves in quadrant 1. So this is going to be the area that we're trying to find, right in there. That's what we're trying to find. So as soon as we have that picture and the question says find the area, that kind of gives us a clue. But the first, if you don't have the picture, if you don't have the graph, it's really hard to just do the math here. You have to, I mean, if you can have a visualization in your head, and as long as you can see that 4 is above, above, purple's above the green. If you could see that in your mind, that's fine, but most of us can't. So drawing the picture is going to be really, really important. So then we're going to draw our integration element. There's our integration element. So we're thinking of that as a random little thin rectangle at x. Little rectangle at x. And we imagine that rectangle sliding through that region. We can imagine like thousands of little tiny rectangles right next to each other. And we want to add the areas of them all up. So we're going to say the area is going to be the sum from 0 to, okay, we need to know this intersection point. Right there, what's that? Okay, so once again, if it's not obvious, we solve the equation. So we set the 2 equal to each other. To undo a rational exponent, you just raise both sides to the reciprocal of that rational exponent. So all we have to do, I'm going to give myself a little more space here. So we're going to raise both sides to the reciprocal, 3/2. Because when you have a power raised to a power, you multiply, and 2/3 times 3/2 is, what is 2/3 times 3/2? 1. So we end up with just an x on the left. On the right, we have to simplify a constant raised to a fractional exponent, 90% of the time, we are going to use the denominator first. 90% of the time, that's the best way to go. So this is the square root, right? The denominator is the root part of the exponent. The numerator is the power part of the exponent. So we're going to take the square root of 4 and then raise it to a power of 3. So square root of 4 is 2. 2 cubed is 8. So that's going to be right over there. That makes sense? So that tells us that this x value at the point of intersection is right there. All right, so how about the integrand then? So what goes in the integrand is the area of that red rectangle. So first we want the height of that red rectangle. And what is the height of that red rectangle going to be?
4 minus x to the 2 thirds.
So we are finding the area of a rectangle. The height is a vertical distance. If you're trying to find the distance vertically, you always do the upper minus the lower y values. The upper y value is 4. The lower y value is x to the 2 thirds. So the area will be 4 minus x to the 2 thirds multiplied by dx. So that whole quantity in here, you can think of this as the area of the rectangle. Or you can think of this as a distance function right here. And the integral of a distance function gives you area. So then we integrate term by term. The integral of 4 is 4 times x. Oh, it's almost time to break. And then we add 1 to this exponent. So we add 3 over 3. Divide by 5 thirds means multiply by 3 fifths. And we go from 0 to 8. Is everyone okay with that? So if we integrate, we add 1 to the exponent. So we're going to take 2 thirds and add 3 thirds to it, getting 5 thirds. And then you divide by 5 thirds, which means multiply by 3 fifths when you flip it. Plug in 8. 8 times 4 is 32. And now we're going to plug in 8 for this x. And once again, we have a rational exponent. The denominator is the root part. The numerator is the power part. So plugging in that 8 right there, the third root of 8 is 2. And then 2 raised to the 5th power is 32. So we're going to have 32 multiplied by 3 fifths. Now what I'm going to do to solve this little arithmetic thing, I'm going to factor out the 32, because then I'm going to have 1 minus 3 fifths. If we factor out the 32, 1 minus 3 fifths is easy to do in our head. What's 1 minus 3 fifths?
2 fifths.
Right? It's going to be 5 fifths minus 3 fifths, which is 2 fifths. So we end up with 64 divided by 5. That make sense to everybody? Any part of that you want another explanation for? Aiden?
So when I did this, I put it in decimal form. Does it matter which form we put it in?
It does matter because as soon as this number becomes a decimal, you're going to approximate. Right? So we don't want to approximate. So in any math course, basically from here on out, if it doesn't say approximate to 2 decimals or approximate to 1 decimal or something like that, then you definitely want to put it in a fraction form. Because a fraction is exact. A fraction is an exact form, and a decimal sometimes when you look at it, you don't know. When someone presents a decimal to you, you don't know. Did they round it off? Right? Is it an approximation? It's not clear when someone presents a decimal to you that it is exact. A fraction, though, is exact. So we always want to leave things in fraction form unless they ask us to throw in an approximation. Yeah, good question. All right, let's take a 10-minute break. And maybe I'll log off and log back on and see if we can maybe not have it flicker in the second half of class. Is there any chance that that really is the key? All right. Pointed out that in that first assignment, quote unquote, that's not graded, which just is a list of the resources in my math lab for that section, you need the Wolfram player in order to open those files. They used to call it the CDF player, and I think now they just call it the Wolfram player. So you'll have to download that if you want to open those little resources. The other thing that's good about the Wolfram player is that they have a version in that list of the MyMathLab links under content. One of them is the interactive textbook, which has a bunch of sliders and things that you can do. In order to open the interactive e-textbook, you have to have that player. If you just open up the HTML version, you can do it on any computer. But if you want to do the interactive textbook or open up any of these links that just sort of download as gibberish, you need that to see the gibberish.
So the multimedias are like more homework or more just like for help?
Just for help.
Okay.
Just for help. Yeah. So the textbook in each section, if you go to the multimedia library, there's a bunch of PowerPoints, there's a bunch of videos, there's a bunch of other things for each section. And so what I tried to do is just grab all the stuff for each section so you didn't have to go hunt for it in the multimedia library. So if you just go to that homework that says not graded, it just has links to videos and links to animations and things. So just extra help. Just extra. So that's why they didn't open originally. And I was in the Math Center this morning with someone, and that same thing was happening, and I didn't remember. Summer was long. Summer was long. Okay, so let's go to wherever we are. So now we are going to find distance between two curves that are oriented horizontally instead of vertically. So the curves that we just did, we had vertical integration elements. So the curves were separated in this direction. Now we want to separate them horizontally. So the idea is that we have rectangles that are on their sides instead of vertical. So we're going to have our orientation is just going to be reversed. It's going to work just fine, but we're going to have rectangles that are sleeping. So these rectangles are going to go horizontal. So we're imagining all these stacked rectangles. Same idea, though. We're going to add up the areas of all those little rectangles to get the total area. Or you can think about integrating this distance function to get the area, however you want to think of it. Now, the height of these rectangles, though, that are horizontal, you don't do upper minus lower anymore. We're going to do right minus left. So we'll take the right curve and subtract off the left curve. And so the idea, if you're looking at the x-axis and you want the distance between 2 points on the x-axis, you take the right point and you subtract off the left point, and that gives you the distance between the two. So horizontal is right minus left, vertical is upper minus lower. And so that's what they're showing here. So they're saying, okay, well, the right curve is going to be f of y, and the left curve is going to be g of y. And if we do right minus left, that's going to be the height of our rectangle right there. And then this is going to be the width of the rectangle right there. So we're going to do the same thing that we did vertically. The only thing that's different is that we're using y's instead of x's. That's the only thing that's different. So let's take a look at this first example. So this first example, one thing I noticed right away is that we have an absolute value function. And an absolute value function, like we talked about on Tuesday, is piecewise defined. So if you're going to do any integration with an absolute value function, it's going to turn into two separate integrals. We also notice that, oh gosh, there's symmetry here. So we can actually just kind of forget about the absolute value function. If we can find the area of this upper region, we just need to double it. So is everybody agree that we have symmetry? The absolute value of y function is symmetric about the x-axis. And this parabola is not shifted up or down, it's just shifted to the right. There's a reflection and a shift to the right of the basic horizontal parabola. So that's also symmetric about the x-axis. Does anyone remember how you could determine, if someone just gives you a random equation and they said, is it symmetric about the x-axis? How would you tell?
Even and odd function principles?
That's the idea. So how do we tell if a function is even or odd? Whoa! So
Is highest power in it?
yep, so that's how we're going to be able to sort of get at whether it's even or odd. But there's a mathematical substitution that we make.
For even, isn't it f of x equals negative f of x?
That's for odd.
And then the even one would be f of x equals f of negative x?
Yes. So the idea is this. If we think about vertical functions first, functions of x, if you think of an x value and you think of a negative x value, so 2 and negative 2, 4 and negative 4, 5 and negative 5, x and negative x, if it's even, that means they're going to have the same y value, because that's going to be symmetric about the y-axis. So x and negative x have to have the same y value to be even. So f of x and f of negative x would have to match for it to be even. For it to be odd, f of x and f of negative x will be opposites. So here, if we want to know, if we wanted to say, hey, is this thing symmetric about the x-axis? We would say, oh, well, if you replace this y with a negative y, you get the same result. So if y and negative y give us the same exact simplification, the same exact formula, then it's going to be symmetric about the x-axis. So here I'm thinking, oh, if we go up to y or down to negative y, and we get the same x value, that means it's symmetric about the x-axis. Think of it that way. Okay. Not that important for what we're doing now. Let's review. Okay, so now we're going horizontal, though. So if we're going horizontal, we are going to want to draw a rectangle that... Something didn't break. We're going to draw a rectangle like that. So this is our horizontal rectangle, or often referred to as a horizontal integration element. You're integrating distance to get area. So let's see. We need to know this point of intersection, don't we? Because that's going to be our upper intersection point. So that's our upper y value right there. That, whatever that y value is. So somebody tell me, what is the equation of this red line up here in quadrant 1? What's the equation of that red line? Y equals x, or because we're dealing with functions of y, we'd say x equals y. And what about this red one down here? X equals negative y. Yeah, good. So x equals y, x equals negative y. We're not going to use the x equals negative y. We're just going to use the upper one here. So the area is 2 times. And we just said that, oh, we didn't actually find that intersection point yet, but can we do it by inspection? Do we know what that value, so we're looking for y coordinates. Do we know what that y value is? So if we set these two equal to each other, let's do it over here somewhere. So we're going to set y equals 2 minus y squared. So if we put everything on one side, which is what we do with a nonlinear equation, and then we factor it, so set them equal to each other, push everything to one side because it's nonlinear, then we're going to factor it. we want the bigger constant to go with the plus sign because the number inside the middle coefficient is positive. So we end up with y equals 1 or negative 2. So what is that y value? Up here? 1. So what does that make this y value down here? Who said negative 1? That was fast. Usually people say negative 2. But you're right, that is negative 1. What is that negative 2 representing? Anyone know what the negative 2 is representing?
An imaginary value?
It's not an imaginary value.
The value for the x equals y, not the x equals negative y.
So for the x equals y, if we were to imagine the x equals y curve continuing, right? Here, we're only looking at a portion of the curve x equals y. But when we solved this equation, we were just saying, oh, x equals y. And if x equals y more than just in quadrant 1, it keeps on going down. So this line here, if we were to extend it into quadrant 3, it would be meeting that parabola at negative 2 for a y value. All right, so we're there. Let's go ahead and then do right curve minus left curve. So the height of our rectangle, our sleeping rectangle, height is right minus left. So now we are subtracting x values. So this right-hand curve is written as an x value. So if we isolate x, we're thinking of it as an x value. So the x value of this curve right here is 2 minus y squared. The x value of that curve is y. And I guess I wrote parentheses. We don't need parentheses. We're just subtracting off y. dy, and we said 0 to 1. And so this 2 out in front here, this is because we're doubling, right? That's a symmetry 2. The yellow plus whatever's below it. So that's doubling the yellow to get the full intersection area. All right, so now we're just going to integrate. So 2 multiplied by 2y minus y cubed over 3 minus y squared over 2, 0 to 1. Yeah, sure.
I'm sorry, can you explain why we have the 2 on the outside of the integral?
So the 2 on the outside of the integral is to represent the 2 pieces that we're breaking this apart into. The yellow piece and the pink
Because of the
piece.
symmetry, okay.
Because of the symmetry. So that 2 is doubling the yellow to get the combination of the yellow and the pink. When we evaluate this antiderivative here at 0, we get nothing. So we only care about the value of 1. So we get 2 minus a third minus a half. And I'm going to just distribute this 2 because then we'll only have 1 fraction. So then common denominator of 3, we'll get 9 minus 2, which is 7, divided by 3. That'll be our answer. We haven't had a flicker yet. That'll be so bizarre if that actually works. Any questions on any of those pieces? All right, so we got one more of these. Once again, sleeping rectangles, horizontal here. So we're going to have the height of our rectangle be a horizontal distance. Horizontal distances are right minus left. Now, the limits of integration are coming from the intersection points. So there are the 2 intersection points. And we're kind of looking over, and it looks like this one's probably 2. We've got to confirm that, but it looks like 2. And then this one, wherever this one's coming over to. We don't know. So we'll have to solve. So to solve, we set the two equal to each other and then figure out what those y coordinates are. So let's come over to the side and do that. So we have y squared minus 3y plus 12. We're going to set it equal to the other curve. So we've got that. Once again, nonlinear. Nonlinear means shove everything to one side, factor. That's going to give us a few y squareds. 3y squared, plus 3y minus 18 equals 0. Divide out the 3. Factor. So we want the middle to be positive, so we're going to put the bigger factor. We're going to put the larger magnitude with the plus. So y equals 2 or negative 3. All right, so that is our algebra technique to get to those limits of integration, to get to those intersection points. Now we're ready to do our integration. So we'll integrate from negative 3 to 2. And we have to do the right curve minus the left curve. So we can do that, I think, without writing. I think we can do that kind of in our head. So the right curve is the red curve. The left curve is the black curve. So it's going to be negative 2y squared minus y squared. So negative 3y squared. So this is going to be right minus left. This one is right. This one is left. Negative 6y minus 3y. So negative 6y plus 3y will be negative 3y. And then again, right minus left, 30 minus 12, 18. So then we'll do our integration using the power rule. So the power rule for integrals, we add 1 to each exponent and then divide by the corresponding new exponent. Copacetic? And now we have a bunch of miserable arithmetic to deal with. There's no zero. Don't you? We love it when the limit of integration is 0. 2 and negative 3. Ugh. So here we would end up with negative 8, plugging in the 2 first. So negative 8, and then here we get 4 divided by 2, which is 2, times negative 3 is neg 6. 2 there is going to be 36. And then we subtract off. Let's put all this in parentheses just to not, there's too many minuses going on. So let's do our subtraction of the antiderivative at negative 3. So we're going to just plug negative 3 into this whole thing. Negative 3, 3 negatives is going to be negative, times that negative will make it positive. 3 cubed is 27, so we're going to end up with 27. And then this, we're going to get 9 times 3 is 27 over 2, but negative. And then here is positive, but multiplied by a negative, so that's going to be negative, 54?
Yes.
54. So we've got all that. Now, if we had a calculator, we'd just do this real fast. Somebody start typing it into the calculator. $198, 108, 118, 125 over 2?
Yeah. You scroll up a bit.
Yes. Thank you. Is that high enough up? All right, are there any mysteries that need to be revealed? The only mystery so far is that it hasn't flickered yet. Everyone see each of the steps? This is the right curve minus the left curve. Integrate, add 1 to the exponent, divide by the new exponent. Plug in the upper limit, plug in the lower limit, take the difference. Seems fairly okay. All right, let's go to something more exciting. Okay, so we now know how to find areas where we use a vertical integration element and a horizontal integration element. This one you could use either, right? Sometimes it doesn't matter, at least conceptually. Sometimes it's okay to draw a horizontal element, and that could work because you can imagine it going all the way through the whole region without any funny business. You could draw it vertically and it would go through the whole region without any funny business. Is it clear that that did not happen prior? Like this one, we can't use a vertical one. A vertical element, we would have red on top. Like if we drew it here, we'd have red on top, black on bottom, red on top, black on bottom, but over here we'd have red on red. So we can't use vertical. Wouldn't work there. Oops. So this particular one, you could do either. It's not going to matter. So let's have, we have 6 tables. 1, 2, 3, 4. Yeah, let's have these 3 tables. Do it horizontally. And then the other 3 tables do it vertically. So this table over here, purple. This table, these 3 tables over here, purple. And the 3 tables over there are doing green. And we should get the same answer.
Not that fast.
We should get the answer. You're done?
Wait, let me catch on this. I just do it.
Of course somebody
Hopefully y'all come up with the same answer. It's a life or death situation. Anyone that doesn't get the same answer is going to be subjected to 10,000 integrals. Mechanical device. You don't need
the square root, it looks like a line. That's the only reason why that would happen. So limits.
That is so suspicious looking.
So no, probably not. Okay, cool. Cool.
You usually when you have a square root equation, usually the best way to go is to square both sides. Yeah, reminder, if you have a square root equation, the best way to solve it is to square both sides. But then you have to go back and check your answers in the end, because whenever you square an equation, you introduce extra solutions. Extraneous solutions.
What if you just subtract it over x to 6?
So,
Leading square.
I answered that square
You know,
root.
divide by,
Oh, and then you just take.
divide by 2 and square.
This would be what we have. Because
If you end up having to complete the square, divide by 2 and square for the middle term's coefficient.
yes, the entire thing. But if
Yeah, this one you can solve by inspection also.
just write this extra 1/2,
Right?
and you have power 1.
Yeah.
Okay, yeah.
Square root of 1 is 1, 1 cubed is 1.
So,
zero.
Yeah, you see.
Yeah, 0, 1, that works, yeah. Okay. Yeah, 0, 1.
And so you just leave it in 3 minus 1. You don't like, or you could.
So you have here, is this one here?
Yeah,
Remember.
yeah, no, I didn't think about that. That's actually really cool. Okay.
It's like 0.41.
Yeah, it'd be good. It could be.
I just didn't get the actual fraction form. So.
I didn't know you could even do that. I thought, like, if it was a full number. You can guess the answer. At least I can guess. Yeah, that's what I guess.
Yeah, at some point you'll learn to memorize. Wow, not everybody has such a lucky calculator.
How many 12s? Agreed. 5 12s. Agreed. That's yours. Uh-oh, don't look at that. So when you were thinking about integrating that, we're thinking of it as x to the 1/2. So we add 1 to the 1/2 and then divide by that new exponent.
Okay. Okay. So it makes sense if you then that makes
Oh, interesting.
Right, you still got it. So I'm assuming you still way.
Yeah, absolutely. Absolutely. And so then you set that equals to 0, so you'd have x to the 5/2 equals 1. And then you raise both sides to 2/5, and 1 to the 2/5 is still 1.
0.
That's a little more complex.
If you graph the side,
Where
directly
it works.
half on y equals x with equal areas on each side.
Y'all coming up with 5 12s over here? 5 12s? 9 is 5 12?
Those two functions are inverse.
Whatever. Yeah, it's just 1.
Work out fine?
Okay, so you
Pretty
did
good.
it.
Not too bad? All right, 5 12. So there, I did it up there in purple. When you look at this, is there any questions on how we solve to get the zeros? So when we set them equal to each other, if you have a root equation, most of the time it's easiest if you square both sides. And then you solve for x, and then you should go back and check that if you, because when you square both sides of an equation, you can introduce extraneous roots. Not always, but you can. And so then we check. 0 is a solution, both sides, 0, 0, that's true. 1 is also a solution. Those are going to correspond then to the two intersection points. So 0 and 1. So whether you did green or you did purple, you would have an integral from 0 to 1. That's right, by inspection. All right, any questions on the integration here? X to the half, add 1, get 3/2, multiply by 2/3. And then plug in your limits. Okay, last slide for chapter 6, section 2. Oh, there's more trig. Shocking. Volumes, we're going to get to volumes soon. 2 dimensions is so boring. Let's go to 3. Okay, so we again are given a pair of curves. We know how to draw sine very easily. And sine, they're saying just in quadrant 1. So quadrant 1 for sine is going to look like that. From 0 to pi. 0 to pi in quadrant 1. Everyone agree that that's sine of x from 0 to pi? Right, if we went to 2 pi, we'd have the lower lobe. But now, what is this curve right here? What is that curve? It's a parabola. Can everybody see that that's a quadratic? If you distribute the x, you have an x squared minus pi x, so that's a quadratic. And so what we know about, and does that quadratic open up or down? Up, because it's going to have a positive x squared. And what we know about quadratics is that the vertex is right in between the zeros. So the zeros here, this tells us that the zeros are x equals 0 and x equals pi. Well, that's perfect. That's what these 2 points are, 0 and pi. And if we wanted to find the y-coordinate of the vertex, we could, but we don't really care. We just care about the orientation. So this parabola is going to be something like that. Doesn't matter if it's closer to the x-axis or further. It doesn't matter. We just need the orientation here so that we can draw our vertical element and understand what curves on top and what curves down below and how to find the height of this purple rectangle. All right, so area is the integral then from 0 to pi for this one. And then the height of that rectangle is the upper curve minus the lower curve. The upper curve is the sine. So it's going to be sine of x minus this curve we're going to distribute here so that we can integrate term by term. So it's going to be minus x squared plus pi times x. How's that look? So that'll be our integral. That is our setup. Ramble on. Integral of sine is negative cosine. So integrate, sine is negative cosine, x squared, add 1, divide by the new exponent, x, add 1, divide by the new exponent. Then we're going to plug in the pi. Cosine of pi, negative 1. X coordinate at pi radians is negative 1. Then we multiply by negative 1 to get positive 1. Then we get minus pi cubed over 3 plus pi cubed over 2. Minus antiderivative at 0. So now we're going to plug in 0 to this antiderivative. Cosine of 0, 1. And then it's a minus in front, so it's minus 1. And the other two terms are both 0. So we're going to have minus a positive we're gonna have this minus. When we plug in that there, cosine of 0 is positive 1. This is negative 1. So we're gonna have minus a minus 1. So that's gonna end up being plus 1. Minus a minus. That's always the hard part. So 2 minus this other stuff. And this is fine. Like that. Oh, they have the same power. We can combine those. I didn't even notice that. What would the common denominator be? 6. So we'll get a common denominator of 6. It's going to be a pi cubed. And let's see how many we're supposed to have. So this is going to be multiplied by 2. This is going to be multiplied by 3. So we're going to have negative 2 plus 3. So we're going to end up with positive pi cubed over 6.
Wouldn't one of those ones be negative since, yeah.
So when we plug in pi here, we get negative 1 times negative 1, which is positive 1. But then when we plug in our 0 here, we plug in 0, cosine of 0 is 1, so this is negative 1, but we're subtracting off the negative 1 because it's the lower limit of integration. So it turns out to be positive after all. So we can write like that. There's our nice irrational number. Irrational numbers. Irrational numbers are, they can be very cute.
If we didn't recognize they had the same exponent, would we get knocked off for having?
Yeah, something that's probably not something that small.
Okay.
It's a little. But. Okay. Let's go. We've done all this work in 2 dimensions, and we're antsy to jump into 3 dimensions. Now it's kind of like just exciting because we live in 3 dimensions. Like doing all this flat work is kind of boring. Let's go 3 dimensions. So here's where we're going to get to something that's more of this order over here. When you integrate area, you get volume. So integrate distance, you get area. Integrate area, you get volume. So we're going to have this sort of sequence of things. We have a distance function. We integrate it. We're going to get area. We integrate it, and we get volume. So that's going to be very similar to the SVA thing. So if we integrate distance, we get area. We just did a bunch of that. Now we're going to integrate area and get volume. So our goal is to find the volume of these weirdly shaped solid objects. And the idea is if you can find the area of a cross-section, so just like with that last problem, we found a formula for the distance between the curves. Then we integrated that distance. The same idea. If we can find the area of this cross-section, then we just integrate the cross-sectional area and we'll get the volume. So the integral of area will be volume. So that's what they're showing us here. And again, we're not going to get into the nitty-gritty. We're just trying to get the concept. So here we have a cross-section. A cross-section is paper thin. It's got no thickness to it. It's 2-dimensional. Then we take our cross-section and we turn it into a slice. A slice adds a little thickness to it, so it becomes a volume. So this has no volume. That's just area. But then we give it a little thickness. We extrude it. That gives us a thickness. We call that a slice. That's a cross-section. That's a slice. And if we add up all our slices, we are going to get an approximation for the volume. But then we go to the Riemann sum thing and we say, hey, let's take the limit as n goes to infinity. So let's take our slices and increase them until we have an infinite number of slices. And in the limit, the Riemann sum becomes a definite integral. So that's the magic of Calc 1, that the limit of a Riemann sum gives us a definite integral. So there we have it. To find the volume, we just integrate the cross-sectional area. Sounds easy. Sounds easy. Okay, so let's find some cross-sectional areas. So we call this the general slicing method. So we're slicing our solid object right down perpendicular to the base of the object. So there we go. There's our object. And we can sort of, it at least appears that each of the cross sections is a rectangle. It appears like it might even be a square. It's hard to tell exactly. It doesn't really matter. So let's go ahead and look at this cross section. So we're looking at that square-ish object. Maybe it's only a rectangle. Who knows? We'll find out probably. So let's see. They tell us the following. They say this curve right here is root 3 minus x. This line is x equals 2. All right. So the solid, the base, when they talk about the base, they mean the floor of the object.
Will you scroll up real fast? Sorry.
Yeah, absolutely.
Thank you.
Yeah, integral of area is volume. So when they say the base of the object, they mean what's the floor down here, right, in the xy plane. And this strange looking object is sitting on top of it. So we have a solid whose base is the region in the first quadrant bounded by those two curves, and whose cross sections, are squares. They tell us they're squares. So so what I did over here was drew the two boundary curves. Here is the square root of 3 minus x. Here's x equals 2. They said also just look in quadrant 1. And so the shaded region right here, this is the base. That right there is the base. That is the base. And then they say, take a bunch of squares. So if you draw this across the base, now come out of the board and build a square. If you were to draw an element right over here, same thing. Now build a square. And you can see that as you get closer to the origin, the squares are bigger. Okay? We have a representative vertical element right there, that red vertical element. Let's get rid of the purple one. So we've got that red vertical element. If we were to sort of pull it out, we've got this situation. So there's our red square that's coming out of the board. Tell me what this distance is right here. I'm going to call it h just for the heck of it. What is that distance?
The integration formula.
The integration of that would give us something different than just h. Just h. What is a formula for h? When we look at this, what is this distance as a function of x? That red line is,
Square root 3 minus x.
that's it, right? That is, so if I consider this side right here down here, this is the base of the square. So this is square root of 3 minus x. Everyone agree? Right, this function is measuring the distance above the x-axis right there. So that distance is root 3 minus x. And if we're told to build a square, what is this dimension going to be? Same, right? Now, if we want to look at specific, we could say, okay, so the square that's sitting right here, what are the side lengths going to be for this smallest square? When x is 2. That smallest square will be 1 by 1. Right, if we plug in a 2 here, we get a square root of 1, which is 1. So that tells us this height is 1 right here. So we'd have a 1 by 1. If we plug in the 2 there and there, we would get 1 by 1. So the smallest square is 1 by 1. The biggest square is over here, which would be 2 by 2. Because this distance right here is 2. So if we put a square there, it would come out 2, and we'd have a 2 by 2 square. All right, so now this is generalized here, so we want that area of the square. What is the area of that square?
Minus x.
3 minus x, because we're going to multiply the height times the width, right? The base times the height. And if you take a square root and you multiply it by itself, i.e. square it, the square root goes away. So we're going to end up with an area that's 3 minus x. Is that okay? So the area of a square is the base times the height, and if you multiply two square roots together, they cancel out, and you get just whatever's on the inside. All right? So now we know, so let's check. Let's check. Is this formula really true? Well, if we go over here and let x be 2, we would get an area of 1. The 1 by 1 square has an area of 1. If we come all the way to the left, that had a side length of 2. The area of that 2 by 2 square, 4. And if we plug in, wait, oh, crap. Is this height really 2?
No.
No. It's not 2. Okay. What is that height? Square root of 3, right? Isn't that distance square root of 3? Yeah, I just glanced and thought it was, careful thinking. Yeah, this right here, that distance right there is square root of 3. That is square root of 3. So what is the area of that square? 3. If you have root 3 by root 3, you get 3. And if you plug in that x equals 0 down here, we get 3 minus 0, which is 3. So this is the area predictor formula. And we've checked it at the two endpoints, and it was right, so it's probably correct. So then we just integrate it to get the volume. So if we integrate, volume will be the integral of 3 minus x. And our limits of integration were 0 and 2. So then we're just going to integrate that. And that'll be our volume. Yeah. All right. Well, let's take a look at another one. So let's see. So with this one, we've got a curve in the xy plane, this square root of cosine x. You would never be expected to graph that. That's not a common curve that you would need to know how to graph. I would give that to you if you were going to use it on a test. We're going to rotate this region around the x-axis, creating this bullet right here. All right. If you rotate a region around the x-axis, what does every cross-section have to be?
Circle.
Yeah, every cross-section is going to be a disk. Right? The cross-section will be a disk, and we have to find the area of a disk. What's the area of a disk?
Area of a circle.
Area of the circle, pi r squared. Yeah. All right, so here we go. So the area of a disk is pi times the radius squared. Isn't the radius just the function?
Yeah.
If the radius is root cosine. So the area for us is going to be pi times the square root of cosine quantity squared. Well, if we square cosines, if we square the square root, they cancel each other out. So we have pi cosine x. That's going to be the area of the cross-section at x. And so again, we could do those two extreme examples just to check that our area predictor is right. What should be the area if we're all the way over here at the tip of the bullet? If we rotate that around, what's the cross-sectional area? Nil, 0. So if we plug in pi over 2 right there, we should get 0. Cosine of pi over 2? 0. Here is the biggest radius. That's going to create a disk of radius 1. And what's the area of a disk of radius 1 or a circle of radius 1? Pi, right? Just pi r squared. And so if we plug in 0 over here, yeah, we get pi, because cosine of 0 is 1, so we get pi. So our area predictor appears to be right. We checked the two extremes, and it gave us the right answer, so we're going with it. So this is part A. Part A says find an expression for the radius of a cross-section. Find an expression for the radius. Why does that sound so weird? The radius, this is the radius right there. The radius is root cosine x. So this is the more important part here. So there's A. What's the area of the disk? So then the volume is going to be the integral of pi cosine of x dx from, they gave us the limits of integration from 0 to pi divided by 2. Pi is a constant, so it can just jump to the front. And the integral of cosine is sine. From 0 to pi over 2. Sine of 0 is 0. Sine of pi over 2, 1. So the volume of that bullet is pi. All right?
Do we have to solve that?
Solve what?
The integral?
We did solve it.
No, do we have to? It says write an integral.
Oh, good point. You're saying we should follow the instructions explicitly?
Well, because I didn't know if writing it solved.
Yeah, no, writing it does mean just that. Yeah, that's a great point. I will ask you to find the value of it to solve it. But that's a good point. It just says write an integral for the volume of the solid. That's kind of vague. I mean, they want us to solve it. I will want you to solve it. If I don't want you to solve it, I'll say set up. I won't try to trick you with weird little word things. But yeah, I will ask you to solve it. All right, pretty cool though that we can find the volume of an object that doesn't have, a lot of symmetry. I mean, there is symmetry here, but. So this next one, we are taking a pair of parabolas that are intersecting in two spots, and once again, we are going to create squares that are perpendicular to the base. So those two parabolas are intersecting down in the xy plane, and we consider that the base, and those squares are perpendicular to the base. Well, that tells us that this height down here, so that height, I'm measuring from there to there, that height, that distance, whatever letter you want to use, that's also going to be this distance, right? If we're going to build squares, both of those would be h's if we use the letter h. And we know to get this height here, we are going to have to do a subtraction of the parabolas. So we're going to take the upper parabola, which is 2 minus x squared, and we're going to subtract off the lower parabola, which is just x squared. So this is going to give us the height, or the distance between those two red points, which is going to correspond to the base of the square. So now we're dealing with squares that have these dimensions, 2 minus 2x squared and 2 minus 2x squared. So then there's the area. So how do we find the area? Just going to FOIL that all out, square it out. So we're going to get positive 4x squared, and then minus 4x squared minus 4x squared is minus 8x squared, plus 4. Something's wrong with my powers. That should be a 4. That should be a 4. So now we have the area of the square at x. And to get the volume, we are going to integrate the area. We don't know our intersection points yet, unless they're obvious. I can't. Let's see. Yeah, are those intersection points obvious? They don't look super obvious, do they? Looks like 1 and minus 1 maybe. If you plug in a 1 here, you get 1, and if you plug in a 1 here, you get 1. If you plug in a -1 here, you get 1. If you plug in a -1 here, you get 1. So kind of obvious, but we could just do the math. If we want to set those equal to each other, we would say 2 minus x squared equals x squared. So we're going to get 2 equals 2x squared. Oh, I'm not doing it the standard way. I'm doing it the extraction of roots way. Normally with nonlinears, you should pull everything to one side and factor. The one exception where you don't have to do that is if you can isolate the square term on one side. They call it extraction of roots. So this is going to go -1 to +1. And we'll do our quick integration. We get that. So plugging in +1, we're going to get 4/5 minus 8/3 plus 4. Now we're going to subtract off what we get when we plug in -1. So we're going to get -4/5. We're going to get, that's going to be a negative in there, so that's going to be a +8/3. That's going to be a -4. And now we're distributing the minus sign here. So everything's going to be doubled, right? So we're going to multiply 2 by all of this. So we are done. We can do this arithmetic in our leisure. I'll do it before I upload the notes. There we are, week 1, 14 to go. 14 weeks to go. Week 1 of Calc 2 in the books. All right, so I'll stick around. Anyone that has questions, I will stay and make myself available to you. We can do math. We can talk snowboarding, talk biking, talk politics, talk whatever. Or you can just leave me here and I'll stand in this room alone. And see you on Tuesday. So, no flickering in the second half. Is it possible?
I'm gonna report that to IT.
I'm going to report that to IT. That's just crazy. Yeah. Let me hit pause on this recording. Hit stop.